Alright, so it's actually the force of my hand pulling it towards me. That's the centripetal force that is keeping it in circular motion. And that force is, of course, ma, where a is the centripetal acceleration. So the centripetal force is equal to the mass times the centripetal acceleration, which we just said was v squared over r. So we now have several formulas in our toolbox now. We have v equals 2 pi over r. We have 2 pi r over tau is what I meant to say there. We have the acceleration, the centripetal acceleration is v squared over r. And now we know that we can kind of combine what we know about that in forces to say that this is true. So we're getting close to done now. Let's talk about a classical case of something like a car going around a curve. If you have a car and the car is going around a curve, then the tendency for that car, if you're not pushing on the steering wheel, it's going to go straight off the road. Clearly, if there's a bunch of ice here, you're going to go straight off the road. But as you go around the curve, what happens is your centripetal velocity tends to be in this direction, but you need to accelerate towards the center. Towards the center. Centripetal force is always towards the center. Whenever I was pulling the string around in circles, I was always pulling, by definition, towards my hand, wasn't I? There's no other way my hand could pull was other than towards my hand, because that's how the string was aligned. And so we could ask questions like this. Let's say we have a 50-meter radius curve. Let's say I'm going 50 meters per second. And let's ask a question like this. What must the force of friction be to keep me from sliding off the curve? This is a very classical typical kind of problem that you'll get with these kinds of issues. What must the force of friction be? Well, why are we talking about friction? We haven't talked about friction yet. Well, in this case, is there a string pulling this car towards the center? There's not. What's pulling the car towards the center? Well, it's got tires. Those tires are turning, and those tires are pushing against the road, and the road's pushing back, and we call that friction. Friction is pushing the car towards the center. So the centripetal force is actually being provided by friction in this case. So in this case, we know that the friction force is being supplied by the centripetal force. So we take what we already know. The friction force is mu times m times g. And the centripetal force is m times v squared over r. And if we know those things, I think I asked when I set up this problem, I asked something different than what I meant to ask. I think I asked what the force had to be to keep it. What I was meaning to say is, what must the coefficient of friction be? What is the coefficient of friction got to be to keep it on the road? So if we go and start plugging in, this is the coefficient of friction. This is what we're trying to solve for. The mass of the car wasn't given, but we don't care because it's on both sides. We're on Earth, so we can use 9.8. The velocity was given as 50. So 50 squared divided by the radius, which is, conveniently, 50. What's 50 squared over 50? Oh, you're good. You're good. It's 50. That's right. 50 squared over 50 is 50. So we have mu times 9.8 equals 50. So we divide 50 by 9.8, which is essentially dividing it by 10. So we have a mu of about 5-ish, maybe just a hair over 5. In other words, this car staying on the road? No, remember mu's typically are somewhere between 0 and 1. And so this is a car which is doomed. You should probably not be going quite that fast. And so that is, I think, about all we need to do with that kind of example. And so from these formulas, you can probably, and from that example, you can probably kind of figure out what you need to do on just about anything that you're going to encounter with these problem sets.